the law talks about two types of changes: physical and chemical. Let's look at an experiment to verify the part about the physical changes. Let's place some ice cubes in a dish and weigh it. Let's say that the weight is X. If we heat the ice, it will melt and form water. If we weigh the water, we notice that the weight is the same as the weight of ice. This proves that when matter undergoes a physical change, like in this case, the total mass of the reactants is equal to the total mass of the products. Now, let's verify the part about chemical changes.
We'll fill sodium chloride and silver nitride in the two limbs of Landau's tube.
Now, let's seal both the limbs with a rubber cork.
Let's weigh the tube and note the weight. This is the weight of reactants before taking chemical reaction. Now, tilt the tube to mix the solutions thoroughly. Reaction takes place, and we notice that a white precipitate of silver chloride is formed in the tube along with sodium nitrate solution.
Let's weight the tube after the reaction. We observe that the weight remains the same. Thus, we can conclude that when matter undergoes a chemical reaction, the total mass of the reactants is equal to the total mass of the products.
That is, during any chemical reaction, matter is neither gained nor lost.
Hence, this law is also called the law of indestructibility of matter. Now let's look at the next law. Law of definite proportions. As the name suggests, this law deals with the composition of various elements present in a compound. In 1799, Joseph Proust proposed the law of definite proportions. This law states that a pure chemical compound always contains the same elements combined together in the same fixed ratio by mass. For example, the water we get from any source such as river, well, lake, sea, or from any other place always contains hydrogen and oxygen elements in the ratio of 1:8 by mass. Thus, we can say that a given compound always contains exactly the same elements in the same fixed proportion by mass. However, this law does not apply if an element exists in different isotopes, which may form a compound.
For example, if a carbon-12 isotope combines with oxygen to form carbon dioxide, the ratio of carbon to oxygen is 3:8. But if a carbon-14 isotope combines with oxygen, then the ratio of carbon to oxygen is 7:16. Another limitation of the law is that elements may combine in the same ratio, but the compounds formed may be different. For example, the compounds ethanol and dimethyl ether have the same number of carbon, hydrogen, and oxygen atoms, but their arrangement is different. That is, the compounds are different.
In 1804, Dalton proposed the law of multiple proportions. This law states that when two elements combine to form more than one chemical compound, then the masses of one of the elements that combine with the fixed mass of the other element bears a simple ratio. For example, when the elements carbon and oxygen combine, two compounds, namely carbon dioxide and carbon monoxide, can be formed.
As seen in the equation for carbon dioxide, 24 parts by mass of carbon combine with 32 parts by mass of oxygen.
Whereas, when carbon monoxide is formed, 12 parts by mass of carbon combine with 16 parts by mass of oxygen.
These masses of oxygen bear a simple ratio of 32:16 or 2:1. In these reactions, a fixed amount of carbon is combining with multiple proportions of oxygen to form carbon dioxide and carbon monoxide.
Similarly, when sulfur dioxide and sulfur trioxide are formed, the masses of oxygen bear a simple ratio of 32:48 or 2:3. In these reactions, a fixed amount of sulfur is combining with multiple proportions of oxygen to form sulfur dioxide and sulfur trioxide. In 1808, Gay-Lussac put forward a generalization which defines the relationship between volumes of gaseous reactants and products. This generalization is known as Gay-Lussac's law of combining volumes. It states that when gases combine or are produced under similar conditions of temperature and pressure, volumes of reacting gases as well as the products bear a simple ratio to one another.
For example, when one volume of hydrogen reacts with one volume of chlorine, the result is always 2 volumes of hydrogen chloride. Thus, ratio of volumes of reactants and products of this reaction is simple.
Another example is when 1 liter of nitrogen gas reacts with 3 liters of hydrogen gas to produce 2 liters of ammonia gas. Since all the reactants and products are gases, the mole ratio of nitrogen gas to hydrogen gas to ammonia gas is same as the ratio of the volume of each gas participating in the reaction. That is, 1:3:2. In 1811, Avogadro suggested that matter consists of 2 kinds of particles, namely atoms and molecules. He defined an atom as the smallest particle of an element, which can take part in a chemical reaction, and may or may not be capable of independent existence. A molecule is the smallest part of an element or compound which is capable of independent existence. He concluded that since the smallest particle of a gas, which can exist independently, is a molecule and not an atom, hence, the volume of gas must be related to the number of molecules. he proposed a law known as Avogadro's law, which states that under similar conditions of temperature and pressure, equal volume of all gases contains equal number of molecules. For example, 1 volume of hydrogen combines with 1 volume of chlorine to form 2 volumes of hydrogen chloride gas. For this to be true, it would mean that the number of molecules in 1 volume of hydrogen, N, will be equal to the number of molecules in 1 volume of chlorine, N. During the reaction, they will form 2 volumes of hydrogen chloride gas, which will contain N plus N, that is, 2N number of molecules, which means that the number of molecules in 1 volume of hydrogen chloride is equal to N. Thus, proving Avogadro's law. While scientists studied matter and formed the laws of chemical combination, they were unable to answer some questions. For example, why are 2 elements different, or why do elements combine to form compounds? Dalton studied the structure of matter, and in 1808 he proposed a theory to describe the structure of matter. This theory was named after him as Dalton's atomic theory. The theory states that matter consists of extremely small, indivisible and indestructible particles called atoms. Atoms of the same element are identical in shape, size, and mass. Atoms of different elements have different sizes, masses, and chemical properties. Atoms of 2 or more elements combine in a fixed ratio to form a compound. Atoms can neither be created nor be destroyed during a chemical reaction. Chemical reactions involve combination, separation, or rearrangement of atoms. Scientists used Dalton's atomic theory for a century. However, in the beginning of the 20th century, scientists like Sir J.J. Thomson, Lord Rutherford, and Niels Bohr came up with new findings, which revealed some drawbacks in Dalton's atomic theory. The drawbacks of Dalton's atomic theory are: it could explain the laws of chemical combination only by mass, but not by gaseous volumes. It could not explain why atoms of different elements have different masses and sizes. It could not explain how and why atoms of the different elements combine to form compounds. It failed to explain the nature of binding forces between the atoms and molecules, which accounts for the existence of the 3 states of matter: solid, liquid, and gaseous. And it makes no distinction between the ultimate particles of an element or a compound. So, they modified Dalton's atomic theory, and it is now known as the modern atomic theory. Here are the key findings of the theory. An atom is no longer considered indivisible. This means that an atom is a complex structure and is made up of electrons, protons, and neutrons. Atoms of the same element may have different atomic masses. Such atoms are known as isotopes. For example, a chlorine atom may have an atomic mass of 35 and 37. Atoms of different elements may have same atomic masses. Such atoms are known as isobars. For example, a calcium atom and an argon atom have the same atomic mass, that is, 40. From this, we can also conclude that atoms of different elements may be identical in one or more aspects. The ratio in which different atoms of different elements combine may be fixed and integral, but may not always be simple. For example, the elements C, H and O combine to form sugarcane. The ratio of the elements 12:22:11 is fixed and integral, but it's not a simple ratio. The atom is the smallest particle that takes part in a chemical reaction. In nuclear reactions, atoms of an element can be changed into another. For example, atoms of nitrogen can be changed to oxygen through bombardment of alpha rays.
On discovering that matter is made up of atoms, scientists' attention was shifted towards identifying the mass of atoms. Since atoms were small particles and could not be separated, scientists were not able to determine the actual mass of an atom by weighing it. It was possible to calculate the mass of an atom by weighing an element and then dividing the weight by the number of atoms. However, there was no method to count the number of atoms available in an element. In an attempt to find a solution to the problem in the 19th century, Dalton made some assumptions based on Gay-Lussac's findings. Based on Gay-Lussac's findings, Dalton assigned hydrogen a weight of 1. He used hydrogen as a standard for determining the atomic masses of other elements and published the first table of atomic masses. Note that the atomic masses in the table indicate relative mass and not the actual mass of the atoms, which means that the masses of elements is relative to the mass of hydrogen. In 1961, scientists met at the International Union of Pure and Applied Chemistry and decided to use carbon as the standard base. Carbon has 3 isotopes, C12, C13 and C14. Since C12 was found to be the most abundant, it was taken as the standard scale. By that time, due to the advancement of technology, scientists started using a mass spectrometer to calculate the accurate atomic mass of elements. The atomic mass of carbon was determined using a spectrometer and was found to be 12 atomic mass unit AMU. All other atoms were assigned a mass relative to the atomic mass unit of carbon. Thus, the atomic mass of an element is the number of times an atom of that element is heavier than an atom of carbon taken as 12. As carbon-12 is an isotope of carbon, it is represented as 12C. Therefore, one atomic mass unit is defined as a mass equal to 1/12 the mass of carbon-12 isotope. And the value of one atomic mass unit was determined to be 1.66056 multiplied by 10 raised to minus 24 gram. Let's determine the atomic mass unit of hydrogen based on this formula. We know that one atomic mass unit is equal to 1.66056 multiplied by 10 raised to minus 24 gram. The mass of a hydrogen atom was determined using a spectrometer and was found to be 1.6736 multiplied by 10 raised to minus 24 gram. Therefore, in terms of atomic mass unit, the mass of an atom of hydrogen atom is said to be 1.008 AMU. When chemists expressed atomic mass on carbon-12 scale, they named it as unified scale, and the unit was represented as U instead of AMU. Though AMU is still used in most places, chemists now use U as the unit. Hence, we can represent atomic mass of hydrogen as 1.008 or 1U, and that of oxygen as 15.9994 or 16U. We know that when atoms of the same elements possess different atomic masses, they are known as isotopes. Hence, for isotopes, the average value of the atomic masses is considered as the atomic mass unit. For example, chlorine has two isotopes with average atomic masses of 34.97 and 36.97 units respectively. The relative abundance of the isotopes is 0.755 and 0.245 respectively. Relative abundance refers to the abundance isotopes of an element, as naturally found on a planet. Average atomic mass of an isotope is the sum of abundance of each isotope multiplied by the precise atomic mass. Thus, the average atomic mass of chlorine is calculated as 35.46 U. Hence, the average atomic mass was redefined as the atomic mass of an element is the average relative mass of its atoms as compared with an atom of carbon-12 taken as 12U. We can also calculate the average atomic mass using fractional abundances of isotopes of an element. Fractional abundance of an isotope is the fraction of total number of atoms that is comprised of that particular isotope. The formula for calculating an average atomic mass from fractional abundance is fractional abundance multiplied by atomic mass of that fraction. Thus, the average atomic mass will be the sum of the products of fractional abundance of the isotopes and their corresponding mass numbers. For example, neon consists of three isotopes: neon 20, neon 21, and neon 22, which have mass numbers and fractional abundances as shown in the table. The average atomic mass of neon will be calculated 20.179 U. When the atomic mass of an element is expressed in grams, it is called gram atomic mass. Gram atomic mass is also called 1 gram atom of the element. For example, 1 gram of magnesium is equal to its atomic mass expressed in gram, which is 24 gram. Like atoms, molecules are also very small. Hence, their mass cannot be determined by weighing them. Therefore, the molecular mass is determined relative to the mass of carbon atom taken as 12U. The molecular mass of substance, element, or compound is the number of times the molecule of the substance is heavier than 1/12 the mass of an atom of carbon-12. In other words, we can say that the molecular mass of a substance is the average relative mass of its molecules, as compared with the mass of an atom of carbon-12 isotope taken as 12U. The molecular mass of any element or compound can be calculated by adding the atomic mass of all the atoms present in one molecule of that element or compound. For example, the molecular mass of water will be the atomic mass of 2 atoms of hydrogen plus the atomic mass of 1 atom of oxygen, which is 18.02U. When the molecular mass is expressed in grams, it is known as gram molecular mass. Gram molecular mass is also called 1 gram molecule of the substance. For example, 1 gram molecule of water is 18 grams. Lastly, let us look at ionic compounds. Ionic compounds such as sodium chloride or potassium nitrate do not contain discrete molecules as their constituent unit. The ions in such compounds are closely packed in a 3-dimensional structure. For example, in the sodium chloride crystal, an ionic bond is formed between a sodium ion and a chloride ion. However, in its crystalline form, each sodium ion is surrounded by 6 chloride ions. So, we have to calculate the formula mass instead of the molecular mass. Formula mass is the sum of atomic masses of atoms present in one formula unit. Thus, the formula mass of sodium chloride is the atomic mass of sodium plus the atomic mass of chlorine, which is 58.5U. When the formula mass is expressed in grams, it is known as gram formula mass.